Hello everyone and welcome back to another video. Today we're going to talk about absolute value functions and equations. So the first thing that we want to talk about is what is absolute value? What does it look like? And what exactly can we do with it? So first of all, what does it look like? Well, when we have these vertical bars around a number or expression, it just means that we're looking at the absolute value. So here we would say for this first example that we're looking at the absolute value of -3, absolute value of 25, absolute value of 7 minus 15, and the absolute value of a. Now, if we think about the definition of absolute value, really it's just representing the distance from 0 on a number line, and it doesn't matter what the direction is. Another way that we can think about it is that it's really just the magnitude of a number ignoring the sign. So if we're thinking about physics wise, it's just the magnitude of a force ignoring its direction. Now, if we were to put this in plain old terms here, let's say, for example, if there was a person standing right here, and we'll say that this is point A, and this person's going to walk 2 steps in either direction, either to the left or to the right. If we were to describe what's happening with this person, is we would say that this person would end up being 2 steps away from A, regardless of the direction. Okay. So really we're just looking at that distance from 0 on a number line. So again, if we were to represent it this way, and let's say we have -2 and a +2, in this case, I would say that the absolute value of 2 is just 2 because we're 2 spaces away, or 2 units away from 0. And over here, the absolute value of -2 is still 2 because we're still 2 units away from 0, even though we're looking at it from the negative side. One important thing to note is that your absolute value is always going to be positive or 0. So if we're looking at the absolute value of a positive number, it's just going to end up being positive. The absolute value of a negative number is also going to be positive, and the absolute value of 0 is just 0 because we're not moving anywhere. We're 0 units away from 0 here. Now, the part that gets a little bit confusing now is when we look at the official definition of absolute value. So here we can state that the absolute value of A is equal to just a positive A if A is greater than or equal to 0, and the absolute value of A is equal to -A if A is less than or equal to 0. Now, the quickest way to explain this is to just come up with a number as an example. So let's say, for example, if we looked at the absolute value of A, and we said that it's equal to 3. Well, this means that we have 2 possibilities. A can be equal to 3 because the absolute value of 3 is equal to 3. And the second part of this is that A can also equal to -3 because, let me get rid of that. The absolute value of -3 is equal, And on the other hand, if A is equal to -3, then we can say that it's because the absolute value of -3 is also 3. So there's going to be 2 possibilities for whatever's inside of my absolute value function there. Now, I might be getting ahead of myself here, but we can show this as well with a couple of graphs. So if we were to look at y is equal to x, just a simple linear function here, and we have y equals to x running through my origin right there. Basically, we're just showing what happens if we have y is equal to x. So if x is 1, y is 1. If x is 2, y is 2. If x is -1, then y is also -1. Now, if we were to contrast that to y is equal to the absolute value of x, we would see, and I know that we haven't really formally graphed this yet, we would actually end up seeing something that looks like this. We'd see this half of the same graph that we just graphed, but now instead of turning into negative y values, it actually gets reflected upwards, and we get this kind of V shape here. Now, if we were to look at our definition here, all we're really doing is just applying that definition. On this side of our origin, we're looking at when x is less than 0. And on the right-hand side, where x is positive, we're looking at when x is greater than or equal to 0. So that's why absolute value functions or linear absolute value functions will have this type of shape. Now, before we move on, let's talk about evaluating expressions with absolute values. We need to make sure that we're still applying the rules of BEDMAS when we're looking at different types of expressions. So we need to evaluate your expression inside the absolute value sign before we make the value positive. So a good way to think about this, and maybe I'll just pull up an example here. Let's say, for example, we have the absolute value of -3 plus 2 versus the absolute value of -3 plus 2. Well, in the first example here, the absolute value of 3 is just 3. And then we're going to add 2 to it. And that gives us 5. On the other hand here, if we're looking at the inside of this absolute value function, -3 plus 2 is equal to -1. So in this case, we're taking the absolute value of -1, which is just going to be 1. Let's demonstrate that on a couple of our calculators here. So here on the left, we're going to start off with our Casio first. So from our screen here, our mathematics screen, so we want to make sure we're on menu, run math, and here we're going to hit option. We're going to go F6. We're going to scroll over until we see number here. So once we see number, we're going to go ahead and hit F4 or number, and we can see ABS right here for absolute value. And what I would recommend is that we get used to using our brackets here, or parentheses. And for example, our first one, we have -3 plus 2. So let's use our brackets -3. And let's close that bracket because our absolute value is only on the -3. So we're going to add 2 to that answer afterwards, and we end up getting 5. Now, what you need to be careful of is with the second one here, let's go ahead and apply brackets to the entire thing, -3 plus 2. And we can see here that we get an answer of 1, just like we did earlier. On the other hand, if we're looking at a TI 83 or 84, we're going to go ahead from the main screen, we're going to hit math, and we're going to scroll over to numbers. So we're going to scroll over, and we can see we have our absolute value function right here. And this one actually puts the absolute value symbols up. So here for the first example, we have the absolute value of -3. We're going to scroll over, and we're going to add 2. And then to do it again, we're going to unfortunately have to repeat the process. Press math, scroll over to number, first option, enter, and we have -3 plus 2 all inside of your absolute value symbols there. And we're going to press enter, and we get an answer of 1. So just make sure that you guys are really careful using your parentheses on your calculators. On the TI is not as big of a deal because it actually shows you what is inside and what isn't. But on the Casio, it can be a little bit trickier to see if you aren't using your parentheses properly. All right, so let's take some time here and evaluate a few absolute value expressions. Some of them are pretty straightforward, but we'll work through them anyways. So the absolute value of 101 is just equal to 101, pretty straightforward. The absolute value of -400 is just 400. Here we are starting to have some more complex absolute values. So absolute value of 5 is just 5. And we're going to subtract the absolute value of -10. So the absolute value of -10 is just 10. So 5 minus 10 gives you -5. Over here, we're going to work with the expression inside first before we take its absolute value. So 5 minus 10 is just -5. So the absolute value of -5 is just 5. What we want to be careful of here is our order of operations. So we can see that we're going to start off with the inside of our absolute value. Then we're going to multiply. And then we take 6 and subtract whatever is on this side. So we're going to work inside out here. So let's look at what's happening inside. So 6 minus 4 times the absolute value of -6. And now we're going to multiply these two together. Actually, we'll do one more step. we'll have 6 minus 4 times negative 6, or rather positive 6, because the absolute value of negative 6 is just 6. And then we have 6 minus 24, which is equal to negative 18. Over here on the, for question number 6, we got a few different steps here. So we have the absolute value signs around the entire thing. So we can simplify where we can first. So 5 times the times negative 2 squared is just 4. So 5 times 4, and we have plus, let me give myself a little bit more room here, plus 7 times negative 3, so that's going to be minus 21. Let's go ahead and do that, and minus 21, and we have minus 15. So then we have 20 minus 21 minus 15. That gives me a grand total of 20 minus 21 is negative 1. Negative 1 minus 15 gives you negative 16. And the absolute value of negative 15 is going to be 16. So let's move on to sketching absolute value functions, which in my opinion, it gets pretty fun. But before we do that, let's go ahead and talk about how we can write the function of an absolute value. So if we're looking at y is equal to the absolute value of x, we define this as a piecewise function. So there's actually two components or two pieces to these absolute value functions. Typically, the way that we would write this is we would say that y is equal to the absolute value of x. And there's going to be two pieces. So I'm going to use my curly braces there. We can say that the absolute value of x is equal to just positive x if x is greater than or equal to 0. And it's equal to negative x if x is less than 0. So that's basically the same thing here. This is just kind of the big piece that we typically write out. So what that shows us here is we're going to take a look at this portion here. Y is equal to the absolute value of x, so it's going to be just x. So basically, for this portion, we're looking at y is equal to x in this case. So maybe I'll just look at this piece right here. Y is equal to x, and that would be this portion right there. But we're going to ignore the rest of this dotted red line. So y is equal to x would run through that whole thing. So if we were looking at y is equal to x, it would just be that whole dotted red line. But now we're just looking at y is equal to x when x is greater than or equal to 0. And now we want to look at the other piece. So the other piece here, and let me go ahead and highlight it. The other piece here states that it's going to be negative x if x is less than 0. So we're actually looking at this portion here. So if I were to draw another line here, maybe I'll do this in green. So if I were to draw this and outline this whole thing here, we would say that this is y is equal to negative x. But because we're only looking at the portion where x is less than 0, so we would say that this portion here, y is equal to negative x, when x is less than 0. So we're looking at these two pieces and we're just ignoring the dotted lines that kind of run through this portion of the graph where y is a negative value. So we're only taking our positive values here. So in other words, if we were to do this, right, and we were to look at my two lines, I would say, okay, well, y is equal to x, and let's draw that line there. And we're just gonna essentially get rid of our negative portion here. And now we're gonna do the same thing for y is equal to negative x. Y is equal to negative x. And we're essentially just getting rid of this negative portion there. So, and if I could draw my line straight, let's go ahead and do that. And our graph looks just like that. So we're just ignoring that negative portion essentially, depending on which part of the domain we're working in. So a couple more characteristics of absolute value functions. Your domain is just x is an element of all real numbers, and y has to be greater than or equal to 0. So like we said earlier, there are no negative values of y. Your x and y intercepts are just going to be the same right there at the origin in this case. So one important thing before we move on is we want to look at your x-intercepts, and your x-intercepts are going to be a really important piece of your absolute value functions. We can think of this as the point where a graph starts to reflect. So in other words, if I were to draw a quick little sketch here, if we know that we had an x-intercept right here at this point, if our initial graph starts to look like this, then pretty much what we're saying is right where it typically go down just like that, it actually starts to reflect and go back up this way. And again, hence, that's why we get that V shape for this basic absolute value function. So in this section, we're going to go ahead and graph the absolute value function if we are given the original graph. So we can see here that we've got two graphs. We've got graph A and we've got graph B, both with different slopes. So essentially what we're trying to do here is we're trying to figure out a way to make any negative y values positive. So we're really just looking at this bottom part and we are reflecting it upwards. So if we're thinking about this portion right here, that would go into the negative y values. All we're going to do is we're going to reflect it upwards. So it looks more like that. And essentially, if we were to continue on with the second part of our graph, it would just make this V shape. So this blue plus this green would give us our graph of y is equal to the absolute value of f of x. But before we move on and do that, we want to actually figure out exactly what it is we're looking at. But this blue and green is really our end game for this section. So before we get started with y is equal to f of x, we're going to look at slope-intercept form. So slope-intercept form comes from Math 10C, where we have y is equal to mx plus b. There are two sections to this, where m is equal to the slope of your linear equation or your linear function, and your b value is going to be equal to your y-intercept. So to figure out your slope, we're going to need to take 2 points. I'm going to take this one right here, and I'm going to take another one where I know the exact coordinates of. So we've got 3, 0, and we have 5, 4. So we don't actually have to use a slope formula because we have the graph. We can go ahead and look at how many units we're going up. So we're going up 4 units here, and we're moving 2 to the right. So remember that slope is equal to rise over run. So in this case, our rise is 4 and our run is 2. So our slope in this case is just equal to 2. So y is equal to 2x. And our y-intercept is right there. It's at -6. So in this case, b is equal to -6. So y is equal to 2x minus 6 is going to be our slope-intercept form of our formula. So y is equal to 2x minus 6 is going to be our equation of y is equal to f of x. Let's go ahead and write this equation as one function. So really, we're just going to take whatever we just found, and we're going to put that inside our absolute value signs. So the absolute value, or y is equal to the absolute value of 2x minus 6, gives us our equation of y is equal to the absolute value of f of x. And now we want to write this as a piecewise function. And maybe I'll rewrite this in blue just because we're going to differentiate this afterwards. So y is equal to the absolute value of 2x minus 6. So before we can actually put this piecewise function together, we're going to look at our x-intercept. So here we can see that our x-intercept is at +3. So x-intercept at x is equal to 3. So that'll give me my two sections. I'm going to look at two distinct parts of my graph. One, first of all, where x is going to be greater than or equal to. So x is greater than or equal to +3. And then we're going to look at a second section, and that's going to end up looking something like this. So again, I'm just going to give a rough little sketch here. Maybe I'll make it a little better. It's going to look something like this. So after this, we're going to look at a section where x has to be less than 3. So remember, if we go back to our definition of an absolute value function and our previous examples, where we're going to have one where it's greater than or equal to whatever your x-intercept is, and one where x is less than whatever your x-intercept is. So for us here, let's go ahead and write down our function. So we have y is equal to the absolute value of 2x minus 6. And we're going to split this up into two sections. So first of all, we're going to look at the positive portion, right, where 2x minus 6 has to be in this domain of x is greater than or equal to positive 3. And now we're going to look at the negative side of this, where we're going to look at the opposite of whatever we had inside our absolute value. And x is going to be less than 3 in this case. So this is typically the part where students get really confused because we're okay with this positive portion here. We know that the positive portion where we have y is equal to 2x minus 6 is really just going to represent this blue line if I were to extend this down. But the negative portion here, what this is going to represent, it's going to represent the other half of this blue line that we want. We want something that runs through right here, and it's going to look just like that to give us that V-shape graph that we want. Now, where does that come from? Now, if you recall from the previous page, we said that if we were looking at something like y is equal to the absolute value of f of x, there is going to be, or rather not f of x, y is equal to the absolute value of x. We're going to have two possibilities, one where we have a positive x and one where we have a negative x. Now, really, this negative x, when we translate it over here, we're looking at the negative of whatever we have inside of our absolute value signs here. So we're taking the opposite sign of everything that's on the inside, which is why we put everything inside of the brackets. And if we were to expand this out, if we said that y is equal to negative 2x minus 6, and we went ahead and distributed, and it looks like this, we have negative 2x plus 6 because negative 6 gives me a positive. This would mean we have two pieces of information. One, that our slope here, our slope of this new part of our line is going to be negative 2. And over here, your y-intercept is going to be equal to positive 6. Now, what this gives us is the other half of the graph that we're looking for. So this blue part we already have, that's going to be y is equal to 2x minus 6. And over here, what we're going to do is we're going to draw, let me get rid of all of this stuff over here. What we're going to do is we're going to draw the other half of our graph that we want, and maybe I'll do this in green. So we said that we want y is equal to negative 2x plus 6. So we said that our y-intercept is over here, and y is equal to positive 6. And since we have a slope of negative 2, it means we're going to go down 2 and 1 to the right. Down 2, 1 to the right, down 2, 1 to the right. And we're just going to continue that until we hit our x-intercept. We're going to go the opposite direction. We're going to go 2 up, 1 to the left, 2 up, 1 to the left, and we can go ahead and connect our line. Now, the part that's really important to note here is what's contained in our subdomain. So we said that it's going to be the positive portion when x is greater than or equal to positive 3. So we're looking at this portion here when x is greater than or equal to positive 3. And now for this portion in the green, we're looking at everything where x is less than positive 3. So we have two parts here, and pretty much what we're doing is really we're just ignoring everything else that we see here, and this V-shape is our resulting graph. So coming back up to graph B, you can pause the video and try out this graph on your own and try to graph the absolute value of graph B, and then unpause once you're done to check your work. Now we can start taking a look at absolute values with the addition of quadratic functions. Now, before we get into it a little bit more formally, we're going to take a look at a few different examples and just be able to sketch these informally. So what we're looking at here is we want to take a look at our just our usual quadratic function. I don't really care what the function actually is, but I want to look at your x-intercepts here. So we see that we have one right here at negative 3, And we have one right here at positive 3. Now remember what we said about absolute value functions. Nothing is going to exist once it's negative. So essentially we can just follow our original here. So we're just going to trace down this way here. And we're just going to ignore all of this stuff underneath. And then we're going to continue to trace upwards here. So this will be part of our new equation, which is going to be y is equal to the absolute value of f of x. So what happens to this part here in the middle? Well, essentially, rather than going down, we're going to come up. We're going to reflect everything that is here, and we're just going to reflect it upwards. So what I'm going to do here is take a look at my y-intercept, which would be -9 down here. So -9 reflected up is going to be a +9. We can take a look at a couple other points too. We can see here that at +2, when x is +2, y is equal to -5. So when we reflect it upwards, when x is +2, y will be +5. And we're going to do the same thing on this side. And we can just go ahead and create a nice, smooth graph just like that. And that gives us the absolute value of f of x. Here you can just pause the video and quickly sketch out the absolute value functions of each of the originals, and then unpause to check your work. Let's try out an example where we graph something that is not a base linear absolute value function. So we have y is equal to the absolute value of x plus 4 here. So we're going to start by looking at the original function. So you know that y is equal to x plus 4. So that means that our y-intercept is going to be here at 4, and we have a slope of 1. So we can go ahead and put our points down with a slope of 1 coming through there. And we're going to connect them all in a straight line. So it looks kind of like that. So we've got about as straight as we can get there. Maybe I'll just cheat a little bit and use the line function. So there we have y is equal to x plus 4. So typically what would happen here is this actually continues on like that with the dotted line, but I'll just kind of leave that portion out. So now how you draw out the rest of this will really be up to you. Some people like to find the piecewise function first, find your the other piece of the line that's going to look like this. It's going to come down to make a V shape. Some people like to just sketch the graph first. Either way works really, but I'm going to go ahead and find the piecewise function first. So here we have y is equal to the absolute value of x plus 4. So that means we have two pieces to consider. First of all, we have the positive version where we have x plus 4. And we can see here that your x-intercept is at x is equal to -4. So we're going to take this portion right here where x plus 4 is our function only when x is greater than or equal to -4. And now we're going to look at the negative side, and we're just going to put a negative on the outside, put everything here inside of my brackets. And in this case, it's going to be in the domain where x is less than -4. So if we were to expand this portion out, we would end up getting y is equal to -x minus 4. So that would mean that we've got a y-intercept of -4 down here, and we have a slope of -1. So all of this underneath your x-axis, right, everything for your negative y values would not show up. But then as soon as I cross this line here, we can go ahead and start to draw our straight line. So that's what our graph is going to look like. I'm just going to ignore everything underneath here. And that is what our graph, and maybe what I'll do is I'll show you the contrast between these. So we're going to have this blue here. So this blue is -x minus 4. And if we were just to combine everything, now this purple line, and if this were to extend further, we'd end up getting y is equal to the absolute value of x plus 4. Looking at our range here, we have the domain we have x such that x is an element of the real number system. There are really no restrictions on what your x values can be. And meanwhile, for your range, we have y such that y just has to be greater than or equal to 0, and y is an element of the real number system as well. Your x-intercept, again, this is what we did earlier where we had x, your x-intercept is x is equal to -4. You can find this algebraically, or you can find it graphically. Again, if you're trying to find your x-intercept, you just plug in y is equal to 0, just like so. We can just drop your absolute value signs. So just have, 0 is equal to x plus 4, and we just have x is equal to -4. So here we look at another example. We just want to introduce one more definition here. So remember what I said earlier on in the video about the x-intercept being a really important part of absolute value functions? Well, there's more of a formal name. We can call it the invariant point for absolute value functions, which really means it's just a point that does not change. Okay, so for example, if we look at our example here, 2x minus 5, let's solve it algebraically first. So we have 0 is equal to 2x minus 5. We have 5 is equal to 2x. And we have x is equal to 5 over 2. So 5 over 2 would be right here. That's my x-intercept. So that would be my invariant point in this case. Nothing about this point will change, whether it's the original function or the absolute value function. Here you can pause the video and try to graph the absolute value function and then write out its piecewise function as well, and then unpause to check your work. So now what we're going to do is we're going to graph quadratic functions and then incorporate them into absolute values as well. So our first step is to graph our quadratic without using the absolute values. So we have y is equal to -x squared plus x plus 6. There's a couple different ways that we can do this, including factoring, finding your x-intercepts, and so on. We can also use our formula x is equal to -b over 2a to help us find the vertex, and that's what we'll do first. So in this case, we have x is equal to -1 over 2 times -1. So we end up with a positive 1/2 because we have 1 or -1 over -2. So we get x is equal to 1/2. That's going to be our x coordinate. And now what we're going to do is we can plug that 1/2 back into the original here. So we're going to put that 1/2 back into here. And what I'll do is, let's go ahead and do this. We've got y is equal to negative 0.5 squared plus 0.5 plus 6. So we end up getting y is equal to 6.25. So our coordinate from here, we get x is 1/2 and y is equal to 6.25. So it doesn't have to be perfect, but it has to be pretty close. So we have 1/2, 6.25, somewhere about there. And now we want to find those x-intercepts. And again, those will be my invariant points. So they don't change. Those are going to be essentially where lots of cool things happen. So we'll take a look at that in just a second. So let's go ahead and factor first. So first step, we have negative. I'm going to factor out the negative. So we have x squared minus x minus 6. So we end up getting x minus 3, x plus 2. So now what we have are my two x-intercepts. We have x is equal to 3 and -2. So 3 is going to come right there, and we have the -2. One more point that we can also add as well is remember that your c value in a quadratic is going to be your y-intercept. So we can actually add one more point right there if we'd like, and then we can mirror it. It's going to be somewhere right there, and we end up with a nice graph here of y is equal to -x squared plus x plus 6. So you can go ahead and finish off the rest of this So it looks something like that. So let's go ahead and label it y is equal to negative x squared plus x plus 6. So now to graph the absolute value function of the same quadratic, what we're going to do is we're just going to take a couple points that are from below the x-axis and reflect them up. Now, since we did it by hand, it's going to be a little bit tricky because, as you can see, I don't have a very steady hand. So just to show you guys a quick example here, if we're looking at -3 here, and we have a point, let's say we have this point here at -4, we're just going to reflect it up. So at -3, instead of being at -4, we're going to now be at +4. And same thing down on this side. If we're at -4 over here and we're at +4 for x, -4 for the y value, we're just going to reflect it up. So instead of being at a -4 for your y values, we're going to be here at a +4. So again, it's not going to be perfect. It's going to look something like this. And we'll end up with our graph. And if I were to retrace over this, this blue portion is going to be my absolute value function. So the absolute value of x squared plus x plus 6. Now again, the more official way to do this rather than drawing a quick sketch would be to actually create your piecewise function. So let's look at our piecewise function here. So we've got y is equal to negative, absolute value. Y is equal to the absolute value of negative x squared plus x plus 6. And that's going to give me my piecewise function here. We have the positive portion where we just take the original function, negative x squared plus x plus 6. And we're going to look at our two boundaries in just a second, or our two subdomains. But before we do that, let's go ahead and do our negative side. So we're just going to put the negative on the outside. We can think of this as a -1, but we typically don't write the negative. We're going to have, let's put the original, negative x squared plus x plus 6. So we're going to see we just have that negative out on the outside. Now, when it comes to our subdomains, right, we're going to have two essentially restrictions here. We're going to use these x values to help us out. So we know that we have our x-intercepts of 3 and -2. Now, the question to ask ourselves is, when will these portions be positive and when will they be negative? Because we only want to take the positive portions. So when we're dealing with our subdomains here, what we're going to do is look at our graph and figure out where is the positive portion of our graph for each section. So here we can see that the negative x squared plus x plus 6, it was positive in this portion here. So let me go ahead and highlight this. So maybe I'll make that a little bit thicker. So in this portion right there, that was our yellow, right? Or green rather. It's positive between those two values. Now, what two values am I referring to? Well, I'm referring to my two values of my x-intercepts between -2 and +3. So you can see here, all of this would be a positive, or would give us a positive y value rather. So we can go ahead and say that as long as our x value is in between -2 and +3, and yes, it can equal to either one of those values, we're going to have positives or positive y values. Now, on the other hand, looking at this negative portion here, we had our red line. Okay, so our red line, what that would have looked like, remember, if you recall, it would have looked something kind of like this, right? If I were to draw that whole thing out completely, well, we need to ask ourselves, where is the positive portion of this quadratic in red, or this parabola in red? Well, I'm just going to go ahead and erase this portion. And we can see pretty quickly that the positive outputs, the positive y values, are going to actually come in two parts. We're going to have this section right here, and we're also going to have this section. Well, how do I define those two sections? Well, for this first part, we're going to say that x has to be greater than, or rather less than, so we'll go ahead and change the color. X has to be less than -2. And that's going to represent this portion here on the left. To represent this portion here on the right, x has to be greater than 3. So x has to be greater than 3. So we can see how important these invariant points or x-intercepts are when it comes to graphing absolute value functions. Now, before we continue on, I realize that I haven't actually graphed anything on the calculators yet, so let's go ahead and pull those guys up. So looking first, maybe I'll do it on the TI first. We're going to go ahead and go into our graphing section. Let's first graph the individual parts of our absolute value function. So let's graph the positive portion first. So we're going to have negative x squared plus x plus 6. And then we're going to have the negative portion. So we're just going to put a negative in front of the exact same thing. So negative of negative x squared plus x plus 6. Now let's go ahead and graph those two. So you've got the blue, which was the positive portion, and now with the red, we have that negative. All right, so what we're doing is we want to pretend that we're just going to cut off everything underneath here. So it's going to look just like this. So it's going to come down in the red, bounce up in the blue, and then come back up in the red. And we're just going to disregard everything that's down here. So we can go ahead and do this third graph, and maybe we'll do it in a better color. Let's do it in green. So I'm going to come down to, I'll do pink. Why not? So we're going to go ahead. Remember to go to your absolute value function. Let's press math, scroll over to number, go to absolute value, and we're just going to input our function in there, plus x plus 6. And we're just looking for the pink portion to confirm that that's going to be our absolute value function. And you can see that it just bounces down towards your x-intercept, comes up to your vertex, bounces back down to your x-intercept, and then back up. And that pink portion will be your absolute value function. Let's go ahead and do the same thing with the Casio here. So we're going to hit menu, go into graph. And because this doesn't graph it in color, it might be a little bit trickier to see, but we're just going to do the exact same thing. So we're going to hit option, go to number, absolute value, and let's put this in brackets, negative x squared plus x, and then plus 6. So just skip right ahead, went straight to your absolute value function. And maybe I'll have to reset my window here. So I'm going to hit F3, go to zoom standard, let's exit, let's redraw it, and we get the exact same thing as our TI calculator. For this next question, feel free to pause the video, try it out, and then unpause once you're done to check your work. For these next couple of questions, we are being asked to write the piecewise function that represents each graph of an absolute value function. There's going to be 2 possible answers for each. So what we're taking a look at are absolute value functions in the form of y is equal to the absolute value of mx plus b. So the first part here, it's asking us what would happen if m is positive. So in this case, if we're looking at a positive m, it means we're looking at a positive slope. So for this first example, our positive slope is going to be everything that occurs here on the right-hand side of the V shape. So we're taking a look at this line here, and if I could trace along properly, that'd be fantastic. And then for the negative portion, we are looking at everything over here. So for the positive slope, what we're going to do is we're going to take a look at 2 points and figure out what exactly our slope is going to be. So the easiest point to work with is going to be this one right here. We can use 2, 0 as my first point. And my second point, we can just simply use this one right here. This is going to be 3, 2. So from here, let's use our slope formula. M is equal to y2 minus y1 over x2 minus x1. We end up getting 2 minus 0 over 3 minus 2. That gives me a slope of positive 2 over 1, or just 2. So now that we know our slope, we're going to use the formula y is equal to mx plus b to help us figure out what our y-intercept is going to be. Now, of course, using our formula, we know that we're going 2 up and 1 to the right, 2 up, 1 to the right to find our points going towards the right. We could just simply use that and just go 2 down and 1 to the left. And we could see that we're going to end up with a -4. But to prove it algebraically, let's use our formula, y is equal to mx plus b. We can use either one of the 2 points that we had earlier. Let's use the one with a 0. So I've got 0 is equal to mx. So my slope was 2. My x value that we're going to use is also 2, and we're going to try to find b. So in this case, we have 0 is equal to 4 plus b. Let's subtract 4 from both sides, and we get b is equal to -4. Let's clean that up just a little bit. B is equal to -4. Hence, our formula, or equation rather, we get y is equal to 2x minus 4, and that's going to be our absolute value function if m was positive. Now for the piecewise function portion of this, what we're going to do is we're going to split this into the positive and the negative portion. So up top, we're going to start with the positive, and then down here, we're going to have the negative. So over here, we've got the positive, which is exactly what we have on the inside. So we have 2x minus 4. For the negative portion, I'm simply just going to put a negative and then put brackets around the 2x minus 4, just like that. In terms of my subdomain, we're going to have to do a little bit more algebra here. Let's find out what this x-intercept was. So here on the side, my x-intercept, we're just going to simply start off with our original equation, 2x minus 4, and we're going to set that equal to 0 to find our x-intercept. So let's do it over here. 0 is equal to 2x minus 4. Let's add 4 to both sides. And then we'll divide both sides by 2. So we get 2 is equal to x. So that means that our x-intercept is at positive 2. So that tells us where our subdomain is split up. So for our positive portion, we're seeing all the positive values starting at 2 and going towards the right, meaning that it has to be equal to or greater than 2. So we can say, in this case, we have x has to be greater than or equal to positive 2. And then for our negative portion, we can see that we are again approaching 2 here, but it has to be everything less than 2 in this case. Now doing the same thing for a negative slope, we're really just looking at this line here. I'm gonna let you do the legwork on your own. But once we get up to that point, we end up getting an absolute value function of y is equal to the absolute value of negative 2x plus 4. And hopefully what you can see is that really we're just applying that negative to everything here, negative 2x and then plus 4. And really just looking at this line there. And again, if we're doing our piecewise function, we're going to first start off with our positive portion. And then we're going to look at our negative portion. So we have our positive portion, which is exactly just the negative 2x plus 4. And then our negative portion is going to be negative of that negative 2x plus 4. Since we already did the legwork earlier to find our x-intercept, we can just go ahead and say that we are looking, in this case, for all of our positive values. Okay, all of our positive values in the positive case. So negative 2x plus 4 is this portion right here. It is when x is less than or equal to 2, which means that for the negative case, we're really looking at this red line here. And that means we're going to have x has to be greater than 2. Here you can pause the video and try out the example on the right, and then unpause when you're done and check your work. Now if we're looking at absolute value functions, with quadratics, we're going to do the same thing, except we're going to work with one quadratic that's going to have a positive a value, and one where you have a negative a value. Now remember, when you have a positive a value, your parabola is going to open upwards, so we're going to get this kind of shape here. And if it opens downwards, we're going to get essentially this type of shape. So really we're looking at two parabolas that are just reflected over the x-axis here. I'm going to start off this example with the negative a value. And the reason why I want to do that is just so we can kind of highlight where the vertex is first for this example. So first off, let's label our vertex. So our vertex we know is PQ. So in this case, it's going to be 1, 9. That's going to be our P. So P is 1 and Q is 9. And then we're going to find a second point on the line. So for us, let's use something simple. So let's use x, y, and we're going to use our x or our y-intercept rather. So 0, 8. So now we have PQ and x and y. How do we figure out our equation of our parabola? So in order for us to come up with our equation, we're going to look at our vertex form here. So we have y is equal to a times x minus p squared plus q. And we're just going to substitute in all of the values that we found earlier. So we have y is 8. So 8 equals a times x, which we know is 0, minus p, which was 1. So 0 minus 1 squared plus q, which was 9. So let's go ahead and simplify a little bit. 8 is equal to a times 0 minus 1 squared. So that's going to be negative 1 squared, which is a positive a. And that's going to be plus 9. Let's subtract 9 from both sides. And I get negative 1 is equal to a. So for us, this checks out because we want our a value to be negative. So now we can plug that a value back into our vertex form. So we can say that we have y is equal to negative 1, or just negative. And then we're going to have x minus 1 squared plus 9. So now what we're going to do is put that equation into an absolute value. So y is equal to absolute value of negative x minus 1 squared plus 9, and that's all inside of my absolute value function. And now I can split this up into my piecewise function. So what's going to happen here is I'm going to have my positive case here. So my positive case, we can think of this as being my original. So I've got negative x minus 1 squared plus 9. And I'm going to have two sections here. So recall, if this is our original, so that's going to be this parabola looking right here. And we have our x-intercepts already given to us. We can see that we have an x-intercept of positive 2 and positive 4. We can see that the parts of this red section that are positive is really everything that is in between negative 2 and positive 4. So we have our positive case, and we're going to say that x has to be greater than or equal to negative 2. And x also has to be less than or equal to positive 4. So that's going to give us the positive section of our piecewise function. And now we're going to look at the negative section here. So again, the negative section really is just the reflection of whatever's happening here. So if I were to actually draw this all the way, it would look like this. But for us, the negative portion is just the reflection. So we're basically taking everything that is down here. So if this negative 6, or this y is equal to negative 6 point, gets reflected back up, this 3 or negative 3, negative 6 becomes negative 3, positive 6. So really what we're looking at is this whole section here and this whole section. So once again, starting off with our negative portion, let's go ahead and write our function that would describe that. So now this becomes just a positive x minus 1 squared, and that's going to be minus 9. So the reason why we do that, if we think about putting a negative in front of the negative here, just like so, that would get rid of this negative, make it a positive, and that would turn this +9 into a -9. So we're going to have two sections here. We're going to, first of all, look at this part right there. So for us, we would have to describe this part as x has to be less than -2. And then looking at this section over here on the right, we would describe this section as x has to be greater than +4. Now, once again, doing the same thing if a was positive, now we're looking at a parabola that will open upwards. So we're going to get this parabola here. And what we're going to do is I'm going to let you guys handle the work once again. We are essentially just trying to pick two values that are going to work for us. So what we can start off with is just reflect our vertex that we had earlier here. So this 1, 9 is actually here at 1, -9. So we're going to be down here. We can reflect our y-intercept. So we have 0, 8 up here. So our reflected point would be 0, -8. So we've got 2 points that we can use to help us out here. So from there, using those 2 points, we end up with a piecewise function that looks like this. So y is equal to the absolute value of just a positive a x minus 1 squared minus 9. And our piecewise sections, we have the positive portion where we'll have x minus 1 squared minus 9. So remember, this top portion is really just this right here. So we're looking at the two arms, meaning we're looking at that part. And this part, when is it positive? We're looking at it when x is less than or equal to -2, and when x is greater than or equal to +4. And once again, with our negative section, we've got negative on the outside, x minus 1 squared, and we're going to have +9. And essentially, we're looking at all of the points that are in between here. So here we're looking at when x is greater than -2, but less than 4 at the same time. That brings us to the end of this video, where we will explore how to solve absolute value equations next time, both graphically and algebraically. Once again, thanks so much for tuning in. If you have any questions, feel free to leave them in the comments below. Stay tuned for the next video, and I'll see you in the next one.